Hi, everyone. I'm Daniel. I'm part of the cloud platform team at Google. Um, and I'm here to talk a little bit about two of our services, BigQuery and Cloud Machine Learning Engine. I will be as concrete as possible. It will be very hands-on examples. All the things, all the stuff that I show today is available on GitHub. So, and I will give you instructions at the end for how to access it. With that said, quick show of hands. How many people are familiar with Google Cloud Platform? Okay, that's good. How many people are familiar with BigQuery? Pretty good as well. Not as good, but pretty good. And how many in here are like software engineers? Okay, good, good. There's no prerequisite to be a software engineer to follow along with the talk. It won't be that advanced. It would be rather the opposite, an opportunity to show you that it doesn't have to be that complicated. Okay, so we will talk today about how to combine large-scale data analytics with machine learning. And to start off, we will do a little bit of a demo of BigQuery, our analytical engine. But before we get into the actual demo, let's first define what's a petabyte. Okay, we know it's 2 to the power of 50 bytes. We know it's 1,000,000 gigabytes, but that doesn't really say anything, right? It's not very concrete, and we talked earlier that we should be very concrete today. So, what is a petabyte? Or more correct, how big is a petabyte? Well, if you're my generation, you remember the old floppy disks. If you took them and you stacked them on top of each other, they would reach they would be around 3 miles high, or 12 Empire State Buildings, in order to cover a petabyte. Because most people in here, I assume, have a smartphone. You are on a 4G connection, or maybe even faster. If you would get the idea to download a petabyte to your mobile phone, that would take you 27 years. And it is recommended that you have a flat fee. So it's 100 times bigger than the Library of Congress, and the Library of Congress holds every book written in the English language. And it's 50 times bigger than every tweet ever tweeted. And again, in my generation, maybe you think it's kind of sad that the corpus of Twitter is twice the size of the Library of Congress. But yeah, it is what it is, right? But then again, how small is a petabyte? Well, if you're into like DNA sequencing and genomics, just 2 micrograms of DNA can actually hold a petabyte. 1 day's worth of video uploads to YouTube. That's a whole lot of cat videos. And you can also have a petabyte. You just need 200 servers logging 50 events per second for 3 years. And then you're also in the petabyte business. Okay, so let's do a quick demo of BigQuery doing a query over a petabyte big data set. And that doesn't... I think there's like some strange command that will just make the font in the editor bigger and not everything. or I just ruined the demo. Let's see. Okay, that did nothing for me. So, never mind. We have an inner select, a quite stupid one. Never try to do this at your relational database. Your database administrator will hunt you down. You're applying a regular expression over more than 1 billion rows. And you know, a DBA, they live to create indices. And in this case, you will invalidate all the indices, and you will do a table scan. And they will not be happy with that. But BigQuery is not a relational database. Instead, it's a distributed system, so table scan is perfectly fine. It's actually super fast. And in the name of transparency, we will also let you know before you submit this query how much it will process, and then we can also give you an estimate how much it will cost. So this query will process close to 2 terabytes, and as I said, this is a demo query. This is not a query that, well, not many people would do it in production. But let's run it. So yeah, we apply a regular expression in this inner select, and then we do a join just to show you that just because it's not a relational database, you can still support relational semantics. And then on top here, we have a sliding window that is showing a trailing average of the sales numbers. So when we were putting together this demo, it's really hard to find a petabyte in an open data set. It's hard to buy a data set of a petabyte size. So we had to create one ourselves. So this is like shoe sales or something. I click Run Query, and that is not correct because I used a cached query, so I was cheating. It is fast, but it doesn't process terabytes of data in a second. So let's do it again. It should take like at least 20 seconds to process. So what's happening here now is that you don't have to do anything. You don't have to provision a cluster or anything. What you basically are doing is that you rent a couple of thousand cores for 15.6 seconds, and that will then answer your questions. So in order to build an infrastructure that delivers these kind of results, if you would to, but I do not recommend it, but if you were to build it yourself, you would spend millions of dollars and a few man-years on creating this. So let's get back to the presentation. So then we have, what is BigQuery? It's a fully managed petabyte scale enterprise data warehouse. Petabyte scale we just saw, fully managed pretty much as well. You didn't have to do anything, no provisioning of clusters or anything. Just submit your SQL queries and you're ready to go. So how did it start? Internally at Google, we have a problem. We had a problem. People who are in the big data business are probably familiar with Hadoop. The Hadoop algorithm, MapReduce, was invented at Google, and we released a research paper on it in 2004. So our problem was that Hadoop was a little bit too complex and a little bit too slow. We couldn't wait minutes, hours, days in order to get insights out of our data, since we were running a growing ads business. So we had to figure out how can we read terabytes of data from disks in seconds. And we came up with, okay, we need like 5,000 to 10,000 hard drives and read them parallel in order to do that. So that's when we started to build our infrastructure. So at Google, the data center is actually the computer, or they are treated as computers. No one knows where their jobs are executed. You just submit a job to our job manager called Borg, and Borg will determine where you have resources idling, and then schedule the job or run the job immediately depending on the priority. So we have these data centers all over the world, and good for you, we have one in Finland. It will open up for cloud business during this year. I'm not sure that this is the actual one, but let's pretend it is for the sake of the argument. So local data center in the data center actually exists already. We serve YouTube and Gmail and search traffic out of it right now, but it's not yet open for our cloud business, at least not for a couple of months more. But then it is. Okay, so how do we do in order to be able to read a terabyte in a second from like 10,000 hard drives? Well, we build most of our hardware ourselves, like our servers and our network equipment, and everything is built in-house. We're like one of the biggest server manufacturers in the world without selling servers. So this is our network switches, our Jupyter, this generation of Jupyter fabrics. They look like this, and they allow us for a bidirectional petabit network. So that means that we can have 100,000 servers that can exchange information at the rate of 10 gigabytes per second between each other. Or if you want to put it in the same example as we did before with the Library of Congress, these 100,000 servers would be able to read the Library of Congress in 1/10 of a second. That's how fast this network is. And this is basically one of the really unique selling points with Google Cloud, if you ask me. So this is how BigQuery works under the hood. We separate compute from storage, which means that this petabyte network is pretty much faster than a system bus at a local computer. So this means also that we easily can move workloads around in our data centers. You can stream data into BigQuery, or you can do batch uploads. And then you submit your SQL queries, and they will be executed by our BigQuery clusters. So fully managed, no ops, processes terabytes or even petabytes in seconds. It's the economy of the cloud, which means that if you want to do experimentation and live up to the slogan "fail fast," you can do so without being ruined, since you only pay for what you use. Anyone with a little bit of SQL knowledge can utilize BigQuery. So please check it out if you're interested. So let's do another demo with BigQuery. So a search demo on BigQuery. These demos are also available at GitHub. Just search for Query It Smart. Let's start with the Stack Overflow one. So we want to find similar documents. And let's take this one. And we will start. It will probably take between 20 and 30 seconds to do this. What it does now is that it compares feature vectors between these 10 million documents that we have downloaded from Stack Overflow. So that took 18 seconds. And here you can see this is the source document. And then you have the similar documents to the right. So let's go back into the demo and show you what we actually did under the hood. So how to find similar posts on Stack Overflow. What we did was that we downloaded the documents, and we split each document into array of words. Then we extract the signatures, which is the feature vectors for each post. We define user-defined function, which is a way of creating a function in JavaScript that you can then call from within your SQL code. And then you use this UDF in SQL for finding similar documents. So what's the fuss about? Like category matching and keyword matching or these kind of things has been around forever. So instead of just saying that, like, okay, this document has the tag music and Shakira, and this document is probably similar because it has the tags music, Shakira, and something else. We actually calculate a score for each of the documents. So we extract the most important words from the content itself. And then we create a feature vector out of that. So that will look like this, that you will have an ID for each of the document in your corpus. And then you will have an array with the word and its score. So that means that then when you want to compare the feature vectors, you do cosine similarity. So you look at the different vectors and you want to know the smaller the angle between them are, the more similar they are. So then we define a UDF to get the similarity. We don't need to run through this because we will do it in a demo. So how many in here are familiar with Jupyter notebooks or IPython notebooks? A few at least, okay. So it's like a development environment in your browser. We use them as well. We call them Cloud Data Lab. It allows you to, from your browser, interact with our services such as BigQuery or TensorFlow or machine learning engine. So straight from the browser, I can create small blocks of code or whatever text I want. So in this case, I have a SQL query. I will execute this SQL query, and I will just get a few of the documents from Stack Overflow. So Stack Overflow is one of the open datasets that we host in BigQuery. So you see, you get an ID, you get the title, and then you get the body of the document. Okay, so we have the data. Then we want to do some segmentation. So we create one of these UDFs, user-defined functions, and it's a super simple function. The only thing it does is a regular expression here, where it strips out all the tags, and it puts everything into lowercase, and it matches all regular characters. So let's do that as well. So standard SQL query. So now it looks like this. We have the ID of the document, and then we have all the words in the document as one array. Okay? Then we want to calculate the feature vectors, the TF-IDF, which is an algorithm for term frequency, inverted document frequency, or something like that. So it will determine how important a word is, but not in the context of the document itself, but in the context of all the documents in the corpus. So for instance, I or you is probably many times in a document, but that doesn't mean it's important because it's in any document with a high frequency. So this one will strip out all these stop words and assign a score to the other words that we believe actually are important. So now we do this with Stack Overflow documents, but this could have been log files from broken devices. So we have IoT devices sending in log files, and we want to find similar devices that show similar patterns as the ones that has broken down, as a way of mitigating that and being able to maybe switch out devices before they actually break down. So here you get it. So now we've applied the vector arrays, or the feature vectors. So list is an important word here. MySQL is an important word. User is an important word, etc., etc. And then we can do exactly the same search we did in the demo, but straight from here. And in this case, I think I can't remember which one I put in, but I think it is about Microsoft SQL Server. So it took like 15 seconds, I think, when we did it in the user interface, so it should be something similar here. Yeah. So the source document is deleting columns in Microsoft SQL Server, and these are the other documents that are very similar to that one. So this whole thing is created with, I would say, very little code. It's SQL and JavaScript, but it creates something that is so much more powerful than just simple keyword matching. Okay. I need to speed up. So, still we haven't even touched the machine learning part of this. So what we did was that, like, what if we wanted to create the machine learning model, and then instead of using these UDFs for doing like the TF-IDF functions, what if we could use the UDFs to access the model for prediction? So we train a model, and then we learn. Then we show you how to use these UDFs to actually access the model that we download in order to do more human-like predictions based on sense or instinct or what have you. So we will use CloudML engine for this. We will use TensorFlow as the SDK to create a neural net. We will not use hyperparameter tuning, but that's part of the CloudML engine. And just to explain for those of you who don't know what it is, like when I create a neural net, especially with multiple layers, so it's a deep neural net, then I can use hypertuning or hypertune on. It's basically to automate all these configuration knobs. So let's say that I want to have, I don't know how many hidden layers I want to have in my neural net, and I don't know the density of each of the layers. Then I can use hyperparameter tuning for that and specify a range. I would like to have more between 2 and 12 layers, and the density should be between, I don't know, 1 and 10. And then the hyperparameter tuning service will find the optimal configuration for me. Otherwise, I would have to do trial and error for that, which is not a problem right now, maybe, because it will only take a few seconds to train. But if I would like to train on big data sets, and every time I trained it, it took an hour, then it would be very easy, nice to get rid of that step. So, first rule of machine learning, don't build a model if you don't have to. So we provide pre-trained models that are accessible as web APIs via REST calls. Check them out first. If they don't satisfy your use case, then start to look into building your own model. So BigQuery will do the pre-processing in this case, and the feature creation, sorry. Then we will train the model, and then we will also use it to predict stuff. So let's go back into another one. We will try to classify whether a location is in Manhattan or not. So that might seem like an easy thing to do for a human being, but it's kind of hard for a computer. So we will start again by just importing the training data from BigQuery. So in this case, we have a data set from the city of New York, I think. It's all the car accidents in New York. So you can see what we get out of this. You get a timestamp, and then you get which borough or neighborhood it happened in, and then the latitude and longitude for that car accident. But you can also see that we need to fix the data, because it misses some of the rows. They are missing the borough, some are missing lat long, and etc., etc. Then we also want to add a column, which is a binary or a Boolean that says like, it's Manhattan or not. So we know if this is Manhattan or not. So that's what we're doing in this step. We also don't care about if we consider Bronx to be Manhattan, because it's really hard to separate them. At least for me. Oops. Okay. Then one of the powerful things is that we can then import this data into our Python code. So in this example, we import it into a NumPy array. So now we have an array that has a 0 if it's outside of Manhattan, and a 1 if it's in Manhattan. And then we have the lat long. Then we want to look at this will then be our training set. So first we need to do feature scaling so that we have something that are comparable in terms of lat and long. And then we also want to plot the training data. And we do that like this. So you can see Manhattan in blue. You can see like Central Park even, probably because there isn't a whole lot of traffic accidents in Central Park. Then we want to split the data into training data and test data. So 8,000 rows goes into the training data and 2,000 goes into the test data. Split is finished, and then we want to do, now we will create our first neural net. This is like a toy example. No one would do this, but we will use a single layer neural net. So what we want to try to do is we want to fit in a straight line between Manhattan and Brooklyn and Queens and Staten Island, which will work in this example, or not perfect, but semi-perfect. But just to show you how easy it is to go from a single layer to a deep neural net. So now we want to, before we have trained it, we want to check our model, how accurate it is before even starting. Takes a few seconds, and then we'll plot it out. Oops. That was not. Sweet Lord. It shouldn't be like 99 when we start. So let's do it a little bit faster. Okay. I've done something wrong, but I don't really know what. Let's see what happens when we start to train this net. So
it's already conscious and self-learning.
yeah, it's obviously smarter. I created Frankenstein.
And the similarity was reached. Now we have to remember the dates.
Yeah. it's very strange because like you can't really reach over 97% with a single layer in this classification example. So it's, yeah. It messes up the grand finale when you're going to do the deep neural net, and it's going to become better since it's already perfect almost. Okay, never mind. So obviously single layer neural nets also work very well when you want to do this. That was not part of the... they say that demos not work, but obviously they work too well sometimes. So let's do another demo then. So let's restart this little, and we will do a New York City bike forecast. So what we will do now is exactly the same thing. Under the hood, the same thing are happening. We're creating a model. We can extract feature vectors out of that model if we like. We can download the model to Google Cloud Storage, and we can access it from our SQL. And we can specify the conditions on these. These are the public bike stations on Manhattan. So April is good. Thursday, fine, sunny. So one would think that like probably there are more people using the bikes later in the week because there's probably more tourists in New York later in the week. But let's see how this will look. So this will generate a heat map that will be shown over the course of 24 hours. So you can see how the demand is changing during that time. And it will probably take 30 seconds to generate this, which is amazing. It will probably take days in Hadoop, or at least hours. And then you can see here what is happening, and that the demand is changing on the different bike stations. Okay. Going back. So what we did here was that we defined the neural net for the demand forecast exactly the same way as we did in the previous demo, you know, the one that didn't really work. And then we trained that model with machine learning engine. We imported the model to cloud storage, and we used a basic JavaScript function to predict it straight from SQL. So that means that, like, if you can create your library of JavaScript functions, and they can then be available to all the analysts that use whatever. Maybe they use a visualization tool, so they don't really write their SQL, but they drag and drop their SQL, and they can also use these functions. That means that, like, without, or with at least very limited experience from actually writing code, whether it's SQL or JavaScript or something else, you can do quite powerful things with this. Yeah, so this was basically what we did. We created this perceptron code in our JavaScript for predicting. And then we had all the weights and biases downloaded from cloud storage. So what I tried to show you today is that using BigQuery, a service that anyone can access, and machine learning engine and the TensorFlow SDK for creating your models, and I mean the simple design patterns that we have looked at today can actually be applied to a whole lot of other use cases. Like we saw how to predict demand. We could use it for a recommendation engine, like what products are similar to this, without just doing like collaborative filtering. Which are the users? Maybe you have you're a gaming company and you have people cheating, and you could use that and like find similar profiles of cheaters or spammers of your system, similar music taste, or as we said before, IoT devices or whatever kind of devices that are about to break down. Sorry. So, summary: petabyte scale data warehouse. Use the UDFs to analyze the feature vectors. Machine learning engine can then extract these signatures in a much more human way. And it's super easy, and you should definitely try it out. So all the sample code available on GitHub. Search query it smart on GitHub, or ping me, dbt@google.com. Also, thanks to our Japanese friend, Tomoyuki Chikanaga, who actually implemented the query it smart. Thank you.